Mathematical Induction, Section 5.1. Now, let's say we have a robot, and we've taught this robot to do lots of nice things. It can walk around, it can pick objects up, but today we're going to make it do something new. We want to teach it how to climb a ladder. And so to do this, we kind of break this up into two key functions that the robot needs to be able to do. The first is that we need to teach it, we need to program it, how to get on the ladder, right? Robot, find the ladder and get on it. So step one is get on the ladder. This is the same as saying the robot needs to be able to get onto the first rung. After that, we need a program that's going to say a function that we can call that says, hey, if you're on any rung, move up to the next rung. In other words, if you're on the kth rung, climb up to the k+1th rung. And so we can combine these two steps to get us all the way up the ladder, right? The step two here, from any rung climb to the next, combined with the getting on the ladder. So we get on the ladder, then we run this. Now I'm on rung 1, get to rung 2. Now I'm on rung 2, get to rung 3, so forth and so on. We're going to use this same idea to do some proofs. So this proof technique is called the principle of mathematical induction. To prove that a propositional statement Pn, propositional function, I'm sorry, is true for all n in the positive integers, where Pn is a propositional function, we need to do two things. First, we're going to verify that P1 is true. We're going to generically use P1 here. This is the same concept as getting the robot onto the ladder. The inductive step says, assume that I'm on the kth rung, that is, pk is true, and use that knowledge to show that pk+1 will be true. In other words, if the robot's on the kth rung, show that you can get to the next one. Another analogy, another nice way to view this, is think about dominoes. So set up some dominoes. We need to do two key things to be able to show that we're going to knock them all down. The first is that we have to be able to knock that first domino down. And as you can imagine, that process is different. That's not how all the other dominoes are going to be knocked down. You have to actually knock it down yourself. After that, we need to be able to show that all the sequential dominoes, right, all the ones following, are going to knock down the next domino. That is, that the kth domino, arbitrary, generic kth domino, will knock down the k+1th domino. If that doesn't happen, right, if that doesn't hold true for all the k's, then we're not going to knock down all the dominoes. So let's try this out. Let's see if we can show that the sum of the first n integers is equal to n times n+1/2. Remember that our process applies to a propositional function. So pay close attention to the quotes there. The question is about this formula. So Pn is a propositional function. So when you put a value in there, the result is either a true or a false. We're asking, is that equal sign true? So we can never take that equal sign for granted. We can't assume it to be true for everything, right? We're trying to show that it's true for everything, for all the values of k. So often when working through this section, you're going to hear me refer to a left-hand side and a right-hand side, at least when an equals sign is in question here. So in blue there, I have the left-hand side. That is the sum of 1 through n. And the question is going to be, is that equal to that right-hand side, n times n+1/2? So put plainly, the question is the left-hand side equal to the right-hand side? Right? The question is on that equal sign. So that's what we're trying to prove, that it is in fact equal. So let's see if we can use mathematical induction to do this. P1 is true. The sum of the first integers from the first integer, in this case, is just 1. And 1 times 1 plus 1 over 2 is 1 as well. So this is a true statement. 1 is equal to 1. So we've shown now that the robot can get on the ladder. We've shown that the first domino can be knocked down. The inductive step is we assume that pk is true for an arbitrary integer k greater than or equal to 1. So we can't plug in a specific value here. We have to assume that the kth domino has been knocked down. What does that assumption of pk being true actually say? Right? We're on the kth rung. We've knocked down the kth domino. What does that mean? Well, we call this assumption the inductive hypothesis because we're making an assumption. In this case, pk being assumed to be true says that if I sum up the first k integers, that is in fact equal to k times k plus 1 over 2. So we're assuming that that sign, equal sign is there, but we can use that now as a premise. So let's show that pk plus 1 will hold true. So we're trying to show that the sum of the first k plus 1 integers is equal to k plus 1 times k plus 1 plus 1 over 2. That is, if you plug k plus 1 into the left-hand side and the right-hand side of the formula, you get the same answer. So this is where it gets tricky. I can't just plug in k plus 1 and say, look, it looks the same, right? This is true because the equal sign is the question here. I have to get from the left-hand side to the right-hand side without assuming that they're equal. So where to start? Well, there's at least one really powerful thing I can do here, and that is that I do know something about the sum of the first k integers. This is me using the inductive hypothesis. I know that the sum of the first k integers is in fact k times k plus 1 over 2. They are equal by the assumption. So I don't bother the k plus 1. Just the sum of the first k. Whenever we use our inductive hypothesis, I want you to place an IH over that equal sign. This shows that I'm stating that they're equal because of the inductive hypothesis. And now that right-hand side that I'm working with here, I can just do some manipulation to get to the right-hand side of the propositional function. And so what you'll see here is that I transformed the left-hand side into the right-hand side. I didn't just plug k plus 1 into it and say, look, it's equal. I got us from the left-hand side to the right-hand side using only algebraic manipulation and the inductive hypothesis. Therefore, pk plus 1 holds true. Let's say we're asked to find a formula for the sum from 1 to 2 to the n. And we do some of the things that we learned in our chapters about sequences, and we have a guess. Our guess is that it's equal to 2n plus 1 minus 1. Sorry, 2 to the n plus 1 minus 1. So can we show that the left-hand side is equal to the right-hand side? In this case, our basis step is actually 0. So 1 is equal to 2 to the 0 plus 1 minus 1. So P of 0 is shown to be true, right? I have an actual input value, so I can plug that in and actually show its truth value. Next, I move on to the inductive step. I assume pk is true for an arbitrary integer greater than or equal to 0. What does that assumption say? What is if pk was true? What is that trying to tell me? That's the inductive hypothesis. That is that the sum from 1 to 2 to the k is in fact equal to 2 to the k plus 1 minus 1. Now I want to show then that pk plus 1 will hold true, right? I'm on the ladder. I'm assuming I'm on the kth rung. Get me to the k plus 1th. It's useful to write out what this would look like. What am I trying to show? I'm trying to show that the sum from 1 to k 2k plus 1 is equal to 2 to the k plus 1 minus 1. So it's always useful to make this little note yourself. This is what you're trying to get to. So I'm going to start with either the left-hand side or the right-hand side and try to transform it into the other. In this case, I'm going to start again with the left-hand side. And now I get to use the same trick this time. How can I manipulate this? Well, I know something about the sum of 1 through 2 to the k. I'm going to use the inductive hypothesis. Now I can rearrange this sum and do some algebraic manipulation and get to 2 to the k plus 1 minus 1. Therefore, p to the k plus 1 holds true. Mathematical induction can be used for a lot of things. We can use it to prove inequalities. Let's show that n is less than 2 to the n, where n is a positive integer. So we're trying to show the formula is true. That is my propositional function, right? That formula either is true or is false. Basis step, plug in 1. 1 is less than 2, so P1 is true. Inductive step, assume pk is true for an arbitrary integer k greater than or equal to 1. What does that assumption of pk being true tell me? It tells me that k is less than 2 to the k. So now I want to show that pk plus 1 holds true. Again, make a little comment to myself. What am I trying to show? I'm going to try to show that k plus 1 is less than 2 to the k plus 1. So I'm going to start with k plus 1. Staring at it here, what can I do with this? Well, the obvious place to start here is again with the inductive hypothesis. Only obvious after you've stared at it for a while and see that I don't really have a lot else I can do. I know, based on the assumption of pk, that k is less than 2 to the k. And now it's easy to get a little lost. Where am I trying to get to, right? Remind yourself of what that right-hand side looks like. I'm trying to show that this will be less than 2 to the k plus 1. How am I going to get there? Well, we can make any comparisons we want as long as we are using our less than or our equals signs, right? Any sort of manipulation we want. So this is where it gets handy. I have 2 to the k. I'd like to get one more copy of 2 in there, right? Can I double 2 to the k somehow? Well, for all k greater than or equal to 1, 2 to the k is greater than 1. So I can make the statement that 2 to the k plus 1 is less than 2 to the k plus 2 to the k. This gives me double 2 to the k, which is what I'm after to get 2 to the k plus 1. So I've shown that pk plus 1 holds true. Let's show that n factorial is less than n to the n. Again, I start with my propositional function. That is the statement that n factorial will be less than n to the n. Now, this statement is holding true for n greater than 1. So the first one we need to try is 2. Is it true? Is P2 a true statement? 2 is less than 4, so P2 is true. Inductive step, assume pk is true for an arbitrary integer k greater than 1. What does that assumption of pk tell me? It tells me that k factorial is less than k to the k. So I want to show that pk plus 1 holds true. Little note to myself, this is what I'm trying to show. Let's start with k plus 1 factorial. Well, k plus 1 factorial can be written as k factorial times k plus 1. And now I know something about k factorial. I know from the inductive hypothesis that k factorial is less than k to the k. I just need to maintain this inequality sign here. So for all k greater than or equal to 1, I can state that k plus 1 to the k will be greater than k to the k. So I'm going to swap out k to the k with k plus 1 to the k. When I do that, I need to be sure to say that I have increased the size of this. Well, this is the same as k plus 1 to the k plus 1. Therefore, pk plus 1 holds true. We can use it for other things too. We can use it for divisibility proofs. So I'm going to show that 3 does divide n cubed plus 2 to the n, where n is a positive integer. Now, this is where it becomes important to note that we're trying to show divisibility. By the definition here, we do not need to actually divide by 3. Let Pn be the propositional statement that 3 will divide n cubed plus 2 to the n. The basis step is P1. When you plug in 1 into n cubed plus 2n, you get 3. And it's easy to see that 3 will divide 3. So P1 is true. Inductive step, I assume pk is true for an arbitrary integer k greater than or equal to 1. What does that tell me? My inductive hypothesis, what is pk being true? What does that tell me? It tells me that 3 divides k cubed plus 2k. So now I'll want to show that pk plus 1 holds true. And this is where some of the convenient patterns I've been using so far really break down. Right? I can't jump immediately into using the inductive hypothesis or anything like that because there is no left-hand, right-hand side. What I'm trying to show is that if I plug in k plus 1, it's divisible by 3. So let's just start with plugging in k plus 1 into the formula n cubed plus 2 times n. And this is not clearly divisible by 3, at least not to me. I don't see any way to just say, hey, that thing's divisible by 3. So I could distribute the 2, or I could multiply out the k plus 1 cubed. Let's do both of those because I don't really have anywhere else that's clear to start. And when I do that, I start to look around and say, okay, can I manipulate this to somehow use my inductive hypothesis? So I'm going to multiply all these things out, and I'm going to group together the k cubed plus 2k because I know my inductive hypothesis says, whew, that's divisible by 3. So that's kind of a relief. At least that part's taken care of. So now I can focus on the remaining parts here, the 3k squared plus k plus 1 plus 2k plus 2. Well, group those together. This is 3k squared plus 3k plus 3, factor out of 3. Well, now I'm set because it's easy to see that 3 will divide this. It's a multiple of 3. And the whole point of doing this grouping was that k cubed plus 2 times k would be divisible by 3 by the inductive hypothesis. So the whole thing is in fact divisible by 3. So pk plus 1 holds true.